Hey, all right. Okay, so lots of fun things to talk about this week. I think I'm probably going to be doing, hopefully, 2 episodes a week, one of which will be specific to engineering and one of which will be some other software projects, but we'll see. It might change up a little bit. Let me change tools. Uh, but after the introductory knowledge graph episode and sort of the tangent into Reynolds transport theorem with railway systems. Today's the real first segment of our engineering fundamentals course series of content, right? So specifically today we're going to be talking about units and measurement. Um, this is kind of funny and incredibly useful once you wrap your mind around how units work and how they interoperate. But I'm going to take a step back for a moment and beyond simply the idea of taking measurements with tools and identifying specific properties or specific quantities, I want to think about first sort of the physical bases for what units are. And of course, we might as well start with, as one does, relativity and quantum, right? Doesn't that start at the very beginning, except not? Um, let's think about three sort of very key dimensions that almost everything else is measured in. We'll talk a little bit about base SI, which factors into 7 kinds of units. But of those 7, there's 3 that are really sort of, heads and tails above the rest. We'll talk about length. We'll put length on that axis, right? Or displacement, distance. Mass and time, right? So when we talk about 3 dimensions, usually we're talking about 3 spatial dimensions, right? But in this case, let's think about very small lengths versus very big lengths, right? Approaching 0. Very small mass versus very big mass, again approaching 0, small. Very small length units of time, very big units of time. There are something called Planck units, Planck mass, Planck length, etc. That's Planck is the physicist. Fortunately, as engineers, we don't really need to worry about Planck units too much, but that's what happens when it approaches 0, right? So within a certain region here, you're really dealing with quantum limits on knowledge, limits on certainty, limits on sort of probabilistic and deterministic, right? As engineers, we don't really like non-deterministic behaviors, but and then out here at the bounds of the extreme, we start having to deal with relativistic effects. Technically, of course, that's this rate, right? This as speed approaches c. But for the most part, you can think of this as engineers living in this happy Newtonian deterministic universe where we're talking about some quantities of units that are in some happy medium for these fundamental dimensions of mass, length, and time. So those are the 3 fundamental base SI units, in this case meters for length, kilograms, believe it or not typically grams, kilograms for mass, and seconds for time. There are very specific physically based and deterministic ways in which these units are defined, which makes them incredibly useful. And for the most part, conversions to and from these units is well defined. There are a few exceptions that we'll talk about when we get to edge cases. But when you think about units, you can think about units as being some exponential, any given unit that you'll typically use in engineering, though there are some exceptions, will be some exponential combination or product of these, right? So, and where these typically have integer values, sometimes they'll be fractional, but for meters per second, for example, you can express that as meters to the first times second to the negative first, and of course kilograms to the 0, right? So this is a nice generic way to think about most units and refactoring and translating most units that you'll be considering and working with in engineering. That having been said, not only are there a few other base SI units that we'll talk about, there's also some funny beasts. And of course, this is just metric, right? But this is probably good enough for now. Um, it's certainly enough to understand most of the physical properties and behaviors that are relevant to engineering. So when we talk about base SI units, there are SI units and there are base SI units. So KGS, sometimes, or KMS, kilograms, meters, seconds, or MKS, you'll hear different expressions used in different places. MKS here is what we looked at on the other slide, so that's meters, kilograms, seconds. Sometimes you'll hear CGS, like centimeters, grams, seconds, etc. MKS is base SI, and then the others they may be useful even if they're still SI, and under certain circumstances will be sort of variations on that, right? So if you think about things translating in terms of to and from base SI units, um, that can be very helpful as a way to uh, summarize or put together translations that might not otherwise make a lot of sense. Okay, so other base SI units here are going to be things like technically, let's put this over here, current, electric current measured in amperes. Really, the amperes are kind of funny because it's really a count, right? It's an account of electrons, like the literal number of electrons as a flow rate. So really, it's more like a unit charge. But that's what, of course, temperature, in this case, degrees Kelvin for base SI. Quantity, so specifically particle quantity measured in moles. So if you think about these two, like how are they related? Really, it's like a fundamental unit of charge, right, as a quantity. So that's one way to summarize or translate. And then the really funny one, oh, this is what, luminescence, I think? Luminous intensity. How do you abbreviate candela like in CD? That's a weird one. We'll talk about some of the edge cases and how these are more relevant. Of course, beyond length, mass, time, temperature is pretty common to run into, and of course you're always going to need to count things, but if you had some basic chemistry, that's not going to be too crazy, right? So these are our 7 base SI units, and any other units that you'll deal with in engineering can typically be expressed as a combination function of these using that sort of exponential nomenclature I outlined earlier. That having been said, there are some interesting ways in which, speaking of sort of combining them, right, we need to think about operations of specific units. So when we talk about numerical measurements, right, A plus B, where these are some quantities that give us C, obviously this is like arithmetic addition, right? You can perform or you can define operations that are relevant to the unit elements of these expressions, these valuations as well, right? So if you have A kilograms and B seconds, that doesn't make any sense, right? So for addition, the rule here, of course, is that the units must be the same. And then that will lead to units of the same. So that's actually, as it turns out, surprisingly constraining when it comes to fundamental operations. Multiplication is a little bit more interesting, and we'll include division in this, right? So A kilograms times B seconds, or maybe divided by, will actually give you a legitimate unit, right? This is a ratio, kilograms per second, or what have you, and you can easily imagine how that would translate for different expressions. So this places an interesting constraint that you can actually use when you're looking at problems and you're not sure, maybe you don't remember, or So quantities A times B will actually give you a unit that's A, the units of A times the unit of B. So when we think about unit operations, there are special considerations that you have to give. And this, of course, can be particularly problematic when you're assuming or assigning units within, for example, a model or a software model. The computer won't care if you're adding the number 1 plus the number 2, even if that's completely invalid, like if you made a mistake or a bad assumption about what units the first number and the second number are in. So there are some tools. I'll share one of them here with you real quick. In Python, there's something called pint, which does a really good job of not only augmenting specific measurements, specific quantities, variables with measurements, but actually controlling and informing what operations are valid for those measurements or for those variables given what units they have. And that can be very interesting. That can be very useful, especially if you look at the way that it's modeled and the way that's extended within the language. But let's see, I'm talking about operations, and that's a great example of a tool. So let's talk about some of the fun things now, right? The edge cases, as it were. So this may or may not surprise you, but a lot of your edge cases are going to come, or that you'll encounter, are quirky things that have to do with imperial units as opposed to metric. Not all. There are certainly some issues here and there, a little bit hidden when it comes to metric system as well. But let's start by talking about imperial, and in particular, let's start by talking about imperial length. This is actually one of the simpler cases because there is, despite the inexact conversion between many different kinds of units, there is one exact conversion that's useful to remember, and that is 2.54 centimeters is equal to 1 inch. And so if you're worried about precision, or if you can't remember exactly what the route is, one thing that I'll commonly see or commonly use is this is an explicit and exact measurement or ratio, right? So you might convert from yards into inches, into centimeters, into meters, which is a little bit roundabout, right? So inches, centimeters, meters, if you're trying to convert yards to meters. But if you try and remember what like the yards to meters ratio is, that's a lot less precise. It's a lot less exact. So let's actually use this as an example of something called, let's see, should we get to dimensional analysis? We'll push this off. We'll look at dimensional analysis last, but this is actually a really good example of something we can think about for dimensional analysis. The next one, and of course, it's worse. So if you remember this one as a means to convert between imperial length and metric length, then most of the conversions within imperial are worth remembering, like feet in miles, right? What is it, 5278 or something like that, being a great example. Yards at 1,760, I think. 520, let's see. Of course, I know this. Why am I pretending like I don't know this? Feet in a mile, 1760 yards in a mile, etc. So within imperial length is fairly straightforward. It's mostly integer conversions, and so there's no precision concerns. Weight, on the other hand, so the exact conversion that you'll want to remember here is pounds to kilograms, and then again within imperial, 16 ounces is a pound, etc. Right, and then there's all sorts of other, stone. How many stone does it weigh? Hopefully you don't need to worry about that, but you can always look it up if you do. But again, if you can get 2 pounds, you can then convert 2 kilograms using, oh gosh. But this is not the only trap here. No. Is it not exact? It's not exact. Dang it. I thought that was exact. I should know better. Okay, so as of 1959, this is useful. There is an exact conversion, but it's pretty subtle. So this is probably not one that I would memorize. We'll start by putting a little approximation here, right? So 0.453 59237. Hey! So that is kilograms is 1 pound. But there's another gotcha here, and that's when we talk about pounds. Pounds can actually mean different things in imperial. And this is not usually something that most people have to worry about, but it is something that engineers have to worry about. So if I tell you that I weigh 100 or 90, 200 pounds, right? Let's say I weigh 200 pounds. That is not a measurement of mass, right? Kilograms is a measurement of mass. That's not a weight. So mass is not weight. Weight is the force from gravity on a specific mass. So in we would use newtons to describe weight in metric, right? In imperial, it's pounds, but it's a different kind of pounds. So we actually need to specify in imperial whether we're talking about pounds mass. So this is a conversion from kilograms, right? Or if we're talking about pounds force, which is what we would use to describe weight. And these are not the same. There's a conversion factor between those because they're not the same units. But you do have to be very careful in imperial units, and this is particularly problematic in civil engineering where they're still used a lot. So that's the big pitfall in imperial weight. I am curious now. I'm going to go ahead and invert that. Yeah, 2.20462, blah, 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 blah. So approximately 2.2, but not the same thing. Okay, other edge cases. The volume. Volume is a fun one, and there's no more fun part of volume than pints. So this is in metric. This is actually kind of interesting because metric defines what a milliliter to be a cubic centimeter of water. Oh no, sorry, not even just of water. That's exact. So a liter is it 10 centimeters on the side? Yeah, can't remember. So what do we typically use to talk about volume in imperial, right? Well, it depends because there's many different units of volume, and they're very often sort of defined by tradition more than anything else. So I find the most useful way to think about volume in imperial as sort of the atomic unit is fluid ounces. So there is a conversion here that I should have looked up beforehand. Okay, this is okay. US food labeling, it's labeled exactly 30 milliliters, but it can depend on which kind of fluid ounce you're talking about. So why is this useful? Because from fluid ounces, there are integer conversions up to most other units of volume in imperial. So 8 fluid ounces is a cup. And if you have some cooking background, volume might be a little more intuitive for you. Some of these will be familiar. Pints are the tricky one. Let's see, is it 4 cups to a quart, I think? Two pints or 4 cups. Yeah, okay, so 4 cups to a quart, 4 quarts to a gallon. There is no specific definition of pint. So when you order a pint of beer, often what you'll get are 16 fluid ounces or 2 cups. That's a useful thing to remember, and certainly when you look at like a quart is 2 pints, right? You can see that all works out. But when you hear someone, hopefully you'll never use pint in engineering because it is surprisingly diverse in terms of definitions. But from there, you can get to most units of measurement using that scaffolding, um, but starting with sort of what fluid ounces are in that conversion. So what other edge cases do I want to highlight? That's most of the imperial ones. Temperature is obviously an edge case, specifically because there's no, so when we want to convert like meters to centimeters, right, we would multiply because in, there's 100 centimeters in 1 meter to get, some quantity of centimeters. You can't just multiply units through like that with temperature, not if you're talking about Celsius, of course, sort of the Celsius Fahrenheit fun. So I find it's useful to remember 9/5 C plus 32 as the conversion for Fahrenheit, but hopefully, and then you can, it's pretty straightforward to invert that. Hopefully you don't have to deal with that, and you can just convert directly to Kelvin or Rankine. Because these, unlike Fahrenheit and Celsius, of course, are absolutely scaled. So now you can say, degrees Kelvin times, if you look at R, for example, that was it, something. I'm going to mess that up. We'll talk about that when we get to constants. So you always bias towards and immediately convert towards the absolute units if you can. Temperature can be tricky, but all of those things are straightforward compared to one of our dear favorite parts of engineering. So this is, if you remember, one of the funky units we were talking about earlier, right? Like luminous intensity. Radiometry is the devil when it comes to units. And there are several reasons for that. For a given, so there's like, first off, if you ever hear visual magnitude, that's a logarithmic measurement calibrated off of, and there's different forms of this too, like absolute visual minute, apparent visual magnitude. This is actually a logarithmic expression calibrated off of human perception. So it's sort of what your eyes perceive as brightness, and not particularly scientific or helpful. So that's another place where when you see VM, convert out of it as soon as possible. But even then, you have like luminosity, luminous intensity. So for a point source, there may be some energy being emitted. The sun is the classic case. But often what you'll need to do is convert that into a rate, like per solid radian, right? So it's fixed some distance away, and some, there's identical flux some other distance away. So there's some, I don't know, watts per solid radian or what have you. And then just to make things more fun, in radiometry, you're typically looking at energy distributions as a function of wavelength, right? So sometimes you'll even have like watts per solid radian per wavelength, right? So anyway, suffice it to say, even there's like 3 or 4 common different radiometric units, and then there's like at least 3 different permutations of each of those, depending on whether or not you're talking about the solid angular rate and whether or not you're talking about on a per wavelength basis. So if you get into optics, this is a big concern. Thermal management is a concern. For infrared or any sort of sophisticated RF calculation, this is a big concern. And it just suffice to say, you need to be careful about which permutations you're talking about, and make sure you're not, magically converting energy without conserving it. So, speaking of which, now we get to talk about the fun part, which is dimension analysis. And I guess there's at least 2 specific examples that we'll use. We had one earlier, was it miles or yards to meters, right? So this process by which you can multiply units is incredibly important because it's what you can use to back out conversions even when you don't remember what they are. So if you have some unit, units can be fractions as well, so some measurement times some measurement. If it's B on top and A on the bottom, this cancels out, right? And you get B. This is incredibly useful in several different ways. First, it's useful for conversions, but it's also useful for problem solving using dimensional analysis. Let's talk about each of those in turn. And then we'll get to some of the more interesting constants, I think, is how we'll try to wrap this up. So let's talk about conversions, right? Let's say you have 100 feet and you need, or yards, and you need to know how many meters is that, right? So what we'll put together is a chain of conversions as ratios that will eventually, this is sort of like a pathfinding, right? Like how do you get to meters anyways? So first, we know we're going to want to go to, remember that explicit, was it 5-4, right? We're going to use that explicit conversion to make sure we're not losing precision. So we want to go from yards to inches, right? So there's 3 yards. We'll collapse this conversion. So basically what you, it's so easy with units to remember, like, do I multiply by that? Or to mix up, do I divide by that? So for example, in this case, that's wrong. We know we want yards on the bottom. We know we want inches on top. So then the question becomes, you're not changing it. You need to multiply it by 1, right? So these quantities need to be the same. How, so for a given number of yards, how many inches are there? Or for a given number of inches, how many yards are there? So usually it's easier to go one way than the other. So in this case, obviously for 1 yard, there's going to be 36 inches, right? So 36 inches, 1 yard, they're the same thing. You're not changing the measurement at all. So now we know we're going to cancel out something and get inches. So now we can use, we know we want to get to centimeters from inches. The bigger number is the smaller measurement, 2.54 centimeters in 1 inch, right? And then we know we're going to want to get to meters from centimeters. So what ratio makes this the same? Well, there's 100 centimeters in 1 meter. Right, so now we've taken the unit translation and we've used that to back out specifically what the arithmetic expression is. So we know exactly how to evaluate that expression. So in this case, 100 times 36 times 254 divided by 100. So conveniently these cancel out, and it's going to be 36 times 2.54, which is 91.44 meters. I'm always surprised, you know, you typically think of, oh, a yard's like pretty close to being 1 meter, right? I'm always surprised by just how much of a difference there is when you actually do units conversions. So this, since this is exact, this might actually be a useful thing to remember. But if you can't remember it, then you know exactly how to back it out, right? But really the point here is the fact that we can use these ratios and we know exactly how to construct these ratios as a means to convert each step to get the units to cancel out using the operation of units. So let's take another interesting situation. So this is, actually, there's, let's do, watts are pretty interesting, and then we'll do, so we want to do R, we'll do watts, and then we'll do orbital period. So watts are an interesting unit, right? Let's say we have a 100-watt light bulb. What does that mean? Well, a watt is a unit that expresses a rate of energy, right? So the unit of energy is joules, and a watt is joules per second, right? But a joule as a unit of energy is an integrated force, right? A force applied over some distance equivalent. So a joule is a Newton second. Or a Newton meter, sorry. Newton meters per second. A force is a unit of accelerated mass. So kilograms times some unit of acceleration. Acceleration is the second derivative of displacement, so meters per second squared, meters. Right? So this is our force. This is our energy. This is our power, watts, right? So of course now we can actually do a little bit of algebra there to simplify this and come up with kilograms. 1 watt is kilograms meters squared seconds cubed. So we can actually express the definition of watts, if you remember, kg MBSC, right, as one of these exponential fractions, where kg in this case is 1, 2, -3. So if you think about going back to the beginning, those dimensions we had, there's an interesting way that you can sort of think about different units as different spaces within some logarithmic version of those dimensions. And it can give you some interesting physical insights as well. But more to the point, it means that you don't have to memorize as many things, and you can figure out a lot of them just by conducting a little bit of dimension analysis and walking through. Okay, so in this case, a 100-watt light bulb is, you know, you can figure out what that relates to in terms of acceleration or what have you. So there's a couple of other, let's see, I mentioned, so we'll do 2 examples specifically. Let's start with, okay, now let's just do one more example. So in orbital mechanics, there's a tricky expression for what the period of a specific orbit is given specific orbital properties, and it's not an easy thing to remember. So it's the angular rate, so time over 1 full circumference, right? So the actual period multiplied by 2 pi. Maybe we'll start with this. So that's the angular rate. How many seconds does it do? Go on about 1 orbit. There's 2 pi radians and 1 complete revolution. So that's an angular rate. You can imagine multiplying both sides by 2 pi. Square root of, and this is where it gets fun, you need seconds to result from this expression, right? So there's some function of gravitational parameter and semi-major axis in this case. So what exactly is that? Well, you need it to evaluate to seconds, and you need an insight to evaluate to seconds squared. The units of gravitational parameter are, let's say this is meters, this is meters squared per second cubed. Am I messing this up? Oh no! Wow, some expert I am. A cubed divided by u. Okay, so this is meters cubed per second squared. There we go. Units of gravitational parameter. There we go. And that's rooted in or derived from like Keplerian's constant area per time. So in this case, we can evaluate that and verify, like, okay, well, meters cubed is going to be on top, and that's going to be divided, multiplied by the inverse of seconds squared, right? So divided by upside down, that cancels out. Then goes to seconds squared, square root of seconds squared is seconds, right? So if we need to remember what that expression is, we can, so solve for the period, we know a cubed over mu. Fun bit of dimensional analysis there. So, if we want to talk about constants, we're going to do a little bit more. There are some constants that pop up a lot more than others. And there are official lists of like good constants to remember just for engineering or to memorize for tests or what have you. I find one of the most interesting and tricky ones is the gas constant. This may just because a lot of my undergrad was, there are many different expressions for the gas constant, suffice to say. So you'll typically see it denoted as R. And in SI units, that is 8.314, some other things. 314 is a fun thing to remember. Joules per degree Kelvin, mole, right? It's one of the reasons the gas constant is so fun. Like, what kind of unit is joules per degrees Kelvin mole? It can make a little bit more sense if we think about it in other terms. Other expressions that you'll often see are things like, oh gosh, 1.987 calories. And I think those are calories, not kilocalories, but I could be wrong. Per degrees mole. For atmospheric science, 8.206, yeah, these are not exact. E minus 5 meters cubed per atmosphere, degrees Kelvin per degrees Kelvin per mole. So if we look at, just going back to our first week, right? We can solve for why that is, or why it makes sense. So this is typically in moles, degrees Kelvin, volume, pressure, right? So that's one reason that we see the expressions we do. In base SI, there's ways to collapse that using sort of the dimensional math that we saw earlier. We expand them into the base units. But when in doubt, you can always remember that R from nRT is going to be some unit of pressure times some unit of volume divided by some unit of count, right, mole, some unit of temperature. So these are the two that you'll almost always see on the bottom, and then of course there's many different ways to express these, because what pressure is force per unit area, volume is cubed, and then force is kilograms meters per second squared. So let's say 2 meters kilograms meters squared second squared, right? So aren't these fun units to just like juggle around all the time? But this does give it some very interesting invariants in physical laws, right? But for the most part, as engineers, we need to just understand how to move around between them. So this is really the point at the end of the day, is as engineers, we don't really have the luxury of saying, well, I'm only going to work in metric. I'm only going to work in base SI, for example. Instead, and you'll hear stories about like the Mars probe that crashed because some contractor forgot to convert in the units of the interface to report, reporting up to the JPL system or what have you, and thought it was measuring distance Mars in kilometers when it was actually miles or vice versa, right? So there's some very famous stories about how units and precision can have a real impact on engineering projects when they're not properly managed. But at the end of the day, what we really need to understand is we need to be fluent. We need to be fluent as engineers, and we need to be able to move around within those different systems of units. We need to understand where the pitfalls are, and we need to understand useful ways to convert. And so that's why dimensional analysis is such an incredibly powerful and important tool for engineers, is it gives us the flexibility to understand and be fluent in and move around within the space of unit conversions very fluently, and in a way where we can be very rigorous in checking what our calculations are and checking to make sure units are consistent, and checking to make sure we're using the right constants, the right measurements, etc. So that is about it. Let's see, what did we talk about? Physical bases for units and measurements. Talked about base SI. We talked about sort of operations and tools. We talked about imperial and other edge cases. We talked about all the edge cases. Yep, especially radiometry. And we talked about sort of some dimensional analysis tricks. That's probably enough for today. As you can probably tell, this isn't like, no one goes into engineering to study units, but this is something that every engineer needs to be fairly comfortable with. So it's one good reason to lead off with it. Next, this week will probably be some sort of software project, and then we'll get back to the next phase of engineering fundamentals. Have a great day. Take care.